Tēnā koutou katoa. E hara hau I te tangata mōhio ki te kororo I te Reo Māori, engari e tika ana ki mihi atu, ki mihi mai. Ko katagarap te maunga, ko debel yeragang ta awa, ko no tai iwi te iwi, no uropi aku tipuna. He Pākehā au no te pāpaka a Maui, no ahi te reria ki te hua uru, no Fremantle au, e noho ana ahau e nei e te taha o te awa o Ōpawaho. He ahorangi kai te aki whakarongo takomahi, ko Gregor Byrne tako ingoa. No reira, tēnā koutou, tēnā koutou, tēnā koutou katoa. So it's a great pleasure to be invited to take part in this Trans-Tasman online conference. And in that Trans-Tasman spirit, I began with an introduction in Maori, my mihi, about where I'm from in Australia. And in a mihi, it's customary to give your mountain and your river as a way of showing where you're from. And given that as I'm recording this, it's National Reconciliation Week in Australia, it's important to acknowledge that the Katagarap, the Mount Eliza, and the Debel Yeragang, the Swan River, are part of the land of the Whadjuk Noongar people. And I mentioned those landmarks as part of my mihi here just to acknowledge the significance of those places to me. So for the last 15 years, I've lived here in Aotearoa, New Zealand, where I'm a professor of audiology at the University of Canterbury. I'm based in Tukuramahi Ahirakapo, the School of Psychology, Speech and Hearing, and I'm very fortunate to be a member of the New Zealand Institute of Language, Brain and Behaviour, and I'm also a member of the Esdell Moore Centre for Hearing and Balance Research, which is based out of the University of Auckland. So I moved to New Zealand in 2005, straight out of my PhD, to start the Master of Audiology program here in Christchurch. And ever since then, I've had a strong interest in improving the accuracy, efficiency, and the utility of speech tests, which are an integral part of auditory assessment, as we know. So that brings us to the title, Speech, Noise, and the Matrix, Tests of Hearing and Auditory Processing at the University of Canterbury. So I apologise to anyone who's come along to this expecting something about the film The Matrix. Unfortunately, there's absolutely no reference to that whatsoever in this talk. So what I'm going to be talking to you about today are these three tests which we've developed and which we've been working on for some time. So the first is the UCAST-FW, the University of Canterbury Adaptive Speech Test Filtered Words, which is a diagnostic test for the presence of auditory processing disorder in children primarily. The second test is the Digit Triplet Test, which is designed to be used as a screening test for sensorineural hearing impairment. And it's a relatively unusual class of tests in that it can be delivered over the phone or over the internet, which has a lot of advantages. And then the third test I'll be talking about is the UC Auditory-Visual Matrix Sentence Test. This uses sentences. It's another speech and noise test, and it allows rapid assessment of adults and children, not only their ability to hear speech in challenging situations, but also their ability to use visual cues to supplement the auditory signal. So all of these tests are part of a software package that I've written called the UCAST software platform, and that delivers all of these tests within a common framework, a common user interface with common reporting and common calibration modes and so on. So although I wrote the software and developed the main mechanics of each of these tests, we wouldn't have got anywhere at all without the work of the Master of Audiology students and the PhD students who work together to gather the data to back up every part of these tests. So you can see there are about 18 or 19 students here, and if you count the really small buttons on the front panel of the software, there's about the same number of those. So essentially, it's like there's a thesis behind every one of those buttons. It takes a tremendous amount of work and lots of human participants to validate these tests and to make sure that they work in the way that we intend them to. So the first of these tests that I'm going to talk to you about is the Digit Triplets test, which we have developed in New Zealand English, in Reo Māori, the Maori language, and in the Malay language also. So firstly, I'll talk about the development and the evaluation of those tests. And these were performed with a number of really fantastic students whose names are here, and also Robert Fremont from the New Zealand Institute of Language, Brain and Behaviour, and Professor Jeanette King. So the prevalence of hearing loss is estimated at about 19% in New Zealand. And when we look at the number of deafness notifications, there's a higher than expected number that come from Maori as opposed to non-Maori. And we know from a wide variety of research that there are numerous geographic, socioeconomic and cultural barriers that prevent individuals from seeking advice and help hearing loss. And we also know that on average, it's about 7 years between when someone suspects that they might have a hearing problem to when they actually do something about it. So having some sort of hearing screening test that's easily available is a great way of cutting down that time and increasing the ability of someone to get help for their problem. So in order for you to know a bit about how these hearing and noise tests work, I thought I'd give you a refresher on the ear and hearing. And being an auditory physiologist and an audiologist, whenever I get a chance to do that, I'm gonna leap at it. So this is primarily for students. I know all you sort of established audiologists know this, but conferences such as this have a fairly wide audience. So obviously, hopefully all of you students still would know what this is. It's a cross-section of the ear with the inner ear highlighted in green there. The bit on the outside is the pinna. It's the bit that holds the glasses on and funnels the sound down towards the middle ear, which matches the impedance of the air-filled outer ear to the fluid-filled inner ear. The inner ear is embedded in the temporal bone. It's the hardest bone in the body, and you can see the posterior vestibular part and that anterior cochlear part, which we're going to focus on, that bony shell there, the osseous labyrinth. If we crack that open, have a look inside, you can see the spirals weaving around of the three scalae, scala vestibuli, scala tympani, and scala media. And perched between scala tympani and scala media is the basilar membrane that you can see here. And due to the gradation of mass and stiffness along its length, we have preferentially sensitive areas to different frequencies. So when we have a high frequency sound, that vibrates the high frequency end of the cochlea, the base of the cochlea, and low frequency sounds make their way around to the apex of the cochlea where they produce their vibration here. And we can animate that in an incredibly non-physiological way, like you see here, so that the size of that is absolutely ridiculous compared to the reality. Rob Patuzzi likes to describe it as a sort of an atomic shimmer of vibration. The magnitude is so incredibly small. And the reason it's so small is essentially because it's underwater. There's a lot of friction to overcome. I'm sure if you've ever tried running through water at the beach, you'll know that it's really difficult to do that. But fortunately, we have some help in that process, and that help comes in the form of the outer hair cells. So if you have a look down on the basilar membrane, as you can see here, we can see the rows of hair cells sweeping around. If you look very closely over here, you can see 3 rows of outer hair cells and 1 row of inner hair cells. If we look closer at the inner hair cells, you can see the tremendous number of spiral ganglion neurons that innervate each one of these inner hair cells. So we've got this tremendous neural innervation for each of those inner hair cells to make sure that they accurately capture all of the neural activity that's generated by those inner hair cells from each of those different tonotopic places along the basilar membrane, and ensure that gets passed all the way up to the relevant part of the auditory pathways and the auditory cortex. But that's not the interesting part. The most interesting part is obviously the outer hair cells. They're my favorite cells in the body. I spent 5 years of my life studying them. But what they do is not only do they detect the sound as a result of the vibration of their stereocilia, but they input energy back into the basilar membrane vibration, increasing it by a factor of 1,000. And they do that by cancelling friction. So for those of you who have had a trampoline as a kid, you may be familiar with the concept of the double bounce. That's where if you time your bounce just right, you can fire your brother up into the air. So it's like that, but it increases the basilar membrane by vibration by a factor of 1,000, which contributes about 60 decibels to our hearing sensitivity. So not only do we get that increase in amplification, that increase in the vibration by a factor of 40 to 60 decibels, but it's also responsible for our absolutely exquisite frequency sensitivity. So removing that damping, adding that negative damping from the outer hair cells really sharpens the tuning of that vibration. So have a look at how sharp that tuning curve is. It's incredible. So it shows just how narrow a range on the basilar membrane, a narrow range of frequencies that each point on the basilar membrane responds to. And it's really important to have that sharp tuning in order to sort of spatially differentiate the different frequencies that are coming in the auditory signals that we're listening to. And this enables each of those nerves from the inner hair cells to carry information that relates to a very small set of frequencies. And what that does is enable the higher centers in the brain to have a better chance at separating that speech from noise. So I'll say it again, your ability to separate speech from noise is largely dependent on the sharpness of the tuning of the outer hair cells. Okay, so when we look down at the rows of hair cells that you can see there, it's beautiful, it's orderly, they're all in straight lines and they're performing as they should be. But old age, loud noise, ototoxic drugs, and that sort of thing, cisplatin, chemotherapy agents can totally wipe out the populations of outer hair cells, particularly in the high frequency end, and with greater doses extending down to the lower and lower frequencies. So look at what that does to our beautiful sharp tuning curve. It's become rather broad and blunt. So an analogy I like to use is it's the equivalent of playing a lovely melody on a piano with your fingertips and then playing the same thing with your fists. It just it sounds awful. And also, if you lose the inner hair cells as well, then you lose sensitivity altogether. All right, so what we need is, given that about 85% of hearing loss can be traced to the cochlea, if we have a screening test that is able to localize and detect that type of sensorineural hearing impairment, that goes a long way to improving outcomes. So the gold standard for hearing sensitivity at the moment is the pure tone audiogram, with which you're all familiar. And that gives us grades of hearing impairment by telling us the quieter sound that people can hear at specific frequencies in the right ear and the left ear. And you respond by pushing a button. It establishes those psychophysical thresholds, and it's great for diagnostics, but it requires expensive equipment, really expensive equipment. Calibrated transducers that have to be calibrated annually, and highly trained staff such as yourselves. But hearing screening, on the other hand, doesn't seek to establish thresholds. It just makes a pass or a refer decision based on whether hearing is in the normal range or outside of that range. So we have a pass range and a refer range. You can use pure tone audiometry to do that, or you could use an objective test like otoacoustic emissions. But that also, to some extent, does require expensive equipment, calibrated transducers, and trained staff. So are there any alternatives? What about a screening method that people could do at home, for instance? Well, fortunately, essentially what we're after is something that has inexpensive or ubiquitous equipment, uncalibrated transducers, and that can be performed by untrained users. So fortunately, there is such a class of tests. This is the Digit Triplet Tests, which are tests of speech comprehension using digits presented in noise. And they were first developed by Smits in 2004, Cas Smits, for the Dutch language. And there's since been versions in many other languages, including Australian English with Heidi Dillon and Marion Golding. I'll play you an example of what it sounds like. Here's the German one.
Die Ziffern 5, 8, 1.
French.
Les numéros 4, 3, 1.
Here's the British English version.
The digits 5, 3, 1.
So you hear those three digits in noise, and you enter your response on the keypad, whether it's a keypad on a telephone or whether it's on the computer screen using the internet. So how can you have a hearing test that works on the telephone? We know how awful things sound on the phone. Well, fortunately, the way these tests work is because of the unique noise that we use to go with that speech. The custom speech noise, which I'll explain in a bit more detail in a moment, means that the performance on the test isn't greatly affected by the absolute level of the signal or the transducer bandwidth within certain standardized limits, but it is highly sensitive to sensorineural hearing loss, and that your ability to separate speech from noise. And it's been used to screen hundreds of thousands of people throughout Europe and elsewhere. But at the time that we developed this, there simply wasn't anything comparable available in New Zealand. So our aim back in 2011 was to produce a validated hearing screening test in New Zealand English and Reo Māori for delivery via internet and via the telephone. So the sequence of the project looks a little bit like this. Firstly, you've got to record and edit those digit stimuli. You need to synthesize the noise to go with it. You need to perform something called normalization, and that's to make sure that all of the test items are equally difficult. If you get one set of triplets, you want to know that your chance of getting that right is the same depending on whether you've got those digits or a different set of digits. You need to then develop equivalent lists so that if you dial up the test and get one list, you'll get the same score as if you had dialed up a different list. You need to verify that they're equivalent and then establish the relationship between the score someone gets on the test and their level of hearing impairment. And you use that information to set some sort of pass or refer criteria to let the person taking the test know whether they've passed the test or not. And then after all of that's done, you can release the test publicly. So it's a lot of work. On that first step, the recording of the digits and editing, we used Ruth Hope, who was a 26-year-old New Zealand female audiology student at the time. She recorded each of the digits. So there's 3 digits that make up the triplet. She recorded each of them in each position to give a natural intonation contour. So if I choose, let's say the number 3, what you hear is
3, 3, 3. 5, 5.
So you get that natural sounding contour there. And then we concatenate those individual digits together to form a triplet. And then we add a carrier phrase at the front, like the digits. And then we have our clean signal to which we've got to add some noise. So you've heard some examples in those other languages. You might be wondering how we create that unique noise. I'll show you now. So remember, this is Ruth's voice as she recorded the digits. And what we do is superimpose all of those digits on top of themselves about 10,000 times. It sounds like this.
4, 8, 5, 4, 3, 5. 8, 5, 9, 5, 6, 1, 3, 8, 9, 5, 9,
So there you go. So that was Ruth's voice. So I call that Ruth noise. And whenever I hear it, it sounds like a swarm of bees, but I can't help but picture sort of like a room full of 10,000 Ruths all talking at once. But the beauty of this technique is that you get the spectrum of that noise matches the long-term average of the spectrum of that speech. So have a look at these 2 spectra down here. They overlay absolutely perfectly. So what that means is if I pass it through a transducer like the speakers on your computer, that might trim a little bit off the top and a little bit off the bottom, the signal to noise ratio stays the same. If I pass it through a telephone that cuts out everything between or outside of the range of 300 hertz to 3 kilohertz, what I'm left with is something where the signal to noise ratio is still the same. So it's really independent of the bandwidth of the transducer, which is fantastic. So the stimuli maintain their signal to noise ratio when they're filtered, and therefore, that's because the signal and the noise are both affected equally. So we generated the stimuli by selecting triplets from a list and then concatenated those to form lists. We changed the level of them to achieve our desired signal to noise ratio, and then we add the noise. So we have the noise at a constant level. As we go through the test, it's an adaptive test. So we change the level of the signal. So that goes up and down, and then we get a stimulus. And so here you can see an example at 0 dB signal to noise ratio where they're both at the same level. So here it is. This is the front panel of the test, the New Zealand Hearing Screening Test. I'll play you the digits, and then you simply enter the ones that you heard. So
the digits 3, 9, 1.
And so you would enter 3, 9, and 1. We've also developed this in Reo Māori. So we had Nicole Gully was our speaker, and we went through exactly the same process, but in Te Reo to create te whakamātautau, whakarongo o Aotearoa. And this was the first digit triplet test that was created in a non-European Indigenous language. We enter kore, iwa, and rima. All right, so I mentioned it's an adaptive test. It uses a simple one-up, one-down adaptive procedure to find your SRT, the triplet SRT, the speech reception threshold, at which you get about 50% of those digits correct, like so. So in this case, if you have a look here, we throw away the first 7 digits and take a mean of the remaining 20, and we come up with -14 as being that SRT, and that's the person's score. But in order to get results that are really reliable and robust, I mentioned we have to go through that normalization process to ensure that all the digits and all the combinations of digits are equally difficult, and that helps to maximize the sensitivity of the test. So how do we normalize speech tokens? Well, let's say we've got two speech tokens, green and blue, for example. So what we do is we present each of those tokens at many fixed signal-to-noise ratios to create a psychometric function. We do that through with a number of different listeners, and then we average their results and fit a psychometric curve to it like this. So essentially what you can see here is at very good signal-to-noise ratios, you're going to get close to 100% of them correct. At the really poor signal-to-noise ratios, you're going to get all of them wrong. And then somewhere in between, there's a value where you're going to get roughly half of them right. So in the case of the word green here, I don't know if this is the curve for the word green, I just made this up, but it is colored green. This signal, the SRT is at minus 7.3 dB signal-to-noise ratio. Now, if we take the word blue, its SRT is, the 50% level for that word is at minus 10 dB SNR. So that means that each of these signal-to-noise ratios that we present the speech at, blue is always easier to understand in noise than green. So that's a problem for our tests. What we need to do is to make them equally difficult. We need to make, essentially we need to make the harder one easier and the easier one harder. And we do that just by giving it a bit of a signal boost within the noise. So we figure out what the mean is of all the stimuli that we've got and adjust each of the individual stimuli to overlay that mean. And so now here you can see that within reason and particularly at that SRT, they are equally difficult in noise. So we've compensated for that and we call that normalization of that stimuli. All right, and then next you've got to go through and repeat that for all of the tokens in the test with a whole heap of different participants. The reason we do that is that it improves the overall sensitivity of the test. So before normalization, you might have a test slope like this, but after you normalize it, you really sharpen up the slope of the test overall. And a steeper slope means it's more sensitive. It means that a person's hearing loss is going to translate to a greater difference in their test score. It's much more sensitive at responding to their individual hearing abilities rather than just the random vagaries of the stimuli that they happen to get. So here we are for each of the digits in each of those three positions. You can see before normalization, we had quite a spread of difficulties. After normalization, they've bunched up quite nicely. And as a whole, the sharpness of the test given by that red line there, you can see the steepness, the slope has improved greatly by reducing the variance around the midpoint. And next we generated lists of 27 triplets, and when we analysed all of those, you can see that they're all psychometrically equivalent. So that means we've got a great deal of confidence that when you dial up and get a particular list, it's going to be this equally difficult depending on whether you called on Monday or on Wednesday, for example. So here are the results for a test like this. This is a whole bunch of participants, both with normal hearing and varying degrees of hearing impairment. The ones with the green dots are those who have mean average hearing thresholds from 250 to 8K that are below 20. And the red dots are people with hearing thresholds above that. And you can see I've drawn a line there to roughly separate those two. I say roughly, it's actually quite a precise process. To do that, we generate an ROC curve, a receiver operating characteristic. What we're trying to do is be right up in the top corner here to achieve maximum sensitivity and specificity. You can see we got very close to that corner with a pass or refer cutoff of 8.8 dB, minus 8.8 dB that you can see here gives us a sensitivity of 94% and a specificity of 88%, which is pretty good when you compare it to the range of tests that are available internationally. So we were really happy with that. With the Reo version, we had no problem getting Reo speakers to do that normalization process. To make all of those items equally difficult. But when it came to getting the data to validate the test, here's the data for our normal hearing listeners that you can see there. But in Christchurch, we had a great deal of difficulty finding sufficient numbers of hearing impaired Māori to take part in this test. And so here are the hearing impaired data, 23 normals. Our hearing impaired data, we had 4. Right. Okay, so what that means is if I draw a line like this, I've got 100% sensitivity and specificity. It's a perfect test. No. Essentially what it means is we need far more participants to properly validate that test. And we hoped to do it this year. but with COVID, it will be potentially next year. We should get onto that, but there's a bit more work required in order for us to be able to release this Te Reo Māori version of the test. So we're keen to get started on that. But we have been able to release the New Zealand English version publicly. So in 2017, we licensed this test to Triton Hearing, who made it part of their hearing screening app, which is on iPads, on stands throughout pharmacies, throughout New Zealand and the Pacific island of Niue. They take it to field days, which are sort of like agricultural shows, and they screen hundreds of people in those situations. Here are a couple of elderly people giving that screening test a go. And there's also an online version where called the Great Big Hearing Check, and over 9,000 people used that last year. So it's getting a great deal of use. We're really happy with that. What we plan to do now is finish developing the Te Reo Māori version. Here's a bunch of year 10 students who are Māori students giving it a go. But we're really taking a great deal of care to make sure that we use a kaupapa Māori approach to gathering that data. So that's where you have a partnership and a collaboration with the community, so with the end users of the test, and work with them to gather that data in an appropriate way. So we've also developed this test in the Malay language, thanks to my fantastic PhD student, Saiful Jamaluddin, who's now based at the International Islamic University in Malaysia. The reason we focused on developing speech materials for the Malay language is that it's spoken by 270 million speakers, and they have very few speech audiometry materials. So there was a real need to create both screening and diagnostic speech audiometry materials there. And so that's what we did. Here is the Digit Triplet Test in Malay that Saiful developed. It sounds like this.
Nombor 0223.
And the results are absolutely fantastic. So we've got data here on this side for using headphones, and on this side there's the results for using telephones. And you can see for the headphones we've got a 92% sensitivity, 85% specificity, and for telephones we're up to 96% sensitivity and 90% specificity. So absolutely fantastic data, and we're really ready to roll that test out across Malaysia. So it is used clinically within audiology clinics within that particular university, but we're hoping to achieve a more widespread release very soon. But it's also found use in research. So, for example, Suzanne Purdy has used these digit triplet tests in a number of her studies. We hope to achieve that broader public release of the test once the Te Reo Māori version has been validated. And we're also looking at different ways to shorten that test. At the moment, it's 27 trials. It's a little bit long, so we're looking at ways that we can get that a bit shorter. Okay, so I want to move on now and talk about the auditory-visual matrix sentence test that we've developed. And again, this is with an absolutely fantastic bunch of students. Now, this is a speech in noise test, but it's not designed for screening. This is a proper diagnostic speech test. And that's because it's an absolutely vital part of the auditory assessment. It's one of the most common complaints that people with a hearing impairment have when they turn up to our clinics, is that they complain of a difficulty to understand speech in noise. So this work has been carried out once again by a fantastic array of students that you can see here, but also my colleagues Rebecca Kelly-Campbell and our linguist colleague Margaret McLagan. So Carhart's definition of speech audiometry back in 1951 was that it's a technique wherein standardized samples of a language are presented through a calibrated system to measure some aspect of hearing ability. And that's as true today as it was then. However, as you've hoped, we've made a lot of progress in this area in the last 60 years. And I'm not just talking about the move from records, from vinyls to tape to CDs, although that is important. But there's now a large range of speech tests that are designed to measure just about every aspect of hearing and auditory processing ability. Many of these tests are really sophisticated, and they're backed by solid research showing their benefits. But as audiologists, we haven't necessarily been as good at adopting these tests when they become available. If you go to many clinics, you'll find that the speech material that's used in assessments is still composed of monosyllabic words that are presented in quiet at fixed intensity levels in the auditory-alone modality. And this type of testing definitely has its place. But given that we've got so many clients who present with hearing difficulties with sentences that are presented in noisy environments and usually in situations where they can see the person that they're talking to. So these two things don't quite match. So on the other hand, we have matrix sentence tests, which many of you will be familiar with. As the name suggests, they present sentence material. They can be presented in quiet, but they're mainly designed to be used as speech and noise tests. And instead of the method of constant stimuli, they use adaptive algorithms to avoid floor and ceiling effects and to find the speech reception threshold more efficiently. So they're still in the auditory-alone mode until now, of course, and I'll tell you about that in just a moment. But it's one of the few sentence tests that works well with a closed set response method or an open set response method. Its adaptive nature and its simple limited vocabulary means that it's suitable for testing people with any degree of hearing impairment, including people with cochlear implants. And they also allow virtually unlimited repetitions of measurements because there's no memorizing of that test material possible. So with standard recorded sentences, you usually have to wait about 6 months between applications of that test. Otherwise, your test scores will be artificially elevated. All right. So the matrix sentence tests were first developed by Hageman in 1982 for the Swedish language. And they consist of syntactically correct but semantically unpredictable sentences. They sound like this.
Svante tog 12 hela dukar.
I don't know about you, but I found that completely semantically unpredictable. But the format of the test becomes a bit more obvious when you look at the British English version. So here's the British English version here. And what you can see is we've got 5 columns, each of which has 10 options. And the columns are in the form of the name, a verb, a numeral, an adjective, and an object. All right. So
Thomas wants 9 cheap beds.
The British version. Thomas wants 9 cheap beds. And so what we've had is versions of this test created in a tremendous array of languages, a huge number of European languages, and there was a version produced out of the University of Sydney in Australian English that was published in 2017. So I was really excited when I first saw this test demonstrated at a European Federation of Audiological Societies conference in Tenerife in 2009. And so on my return, we immediately set ourselves the goal to record a version of this matrix sentence test for use with speakers of New Zealand English. So we based our version on the British English matrix, but we had to make some changes. The vowels of New Zealand English are continuously evolving, and there's also a wide variety of pronunciations found both geographically across the country and also between generations. So because of that, we had to eliminate those tokens which could be confused by those different listeners, and we replaced them with words that were less prone to confusion and which helped us achieve the appropriate phonemic balance. So there's no, we removed those ones that are likely to cause errors. And what we ended up with was this list here. So this is our matrix. Now, there's no gold standard for the distribution of phonemes in New Zealand English, but what we did was map it to the sentences used to produce the hint, and what you can see is it's a very close match with a couple of exceptions. So the first is that all of our nouns are plural, so we've got an over presentation of S, and we don't have the word the there, and so the phoneme is reduced. But on the whole, it's a pretty good match to a standard New Zealand vocabulary. So this is the final matrix, and we recorded it with a 26-year-old female with a typical New Zealand accent, an accent that was typical for her age. So here's how it sounds.
Amy likes 6 old books. Oscar sees 12 good shirts.
So what I mentioned earlier was one advantage of the matrix format is that it allows virtually limitless sentence material. And that's because although this 5 by 10 word matrix has 50 words, they can be arranged in 10 to the power of 5 combinations. So that's 100,000 possible sentences. Now, obviously, it's impractical to record all of these sentences separately. And even if you did, it would be next to impossible to normalize them to ensure that each of the items was equally difficult. So one solution might be to record each of those 50 words separately and splice them together, but that can sometimes sound a little bit disjointed. But the approach that was developed by Kirsten Wagner and colleagues at the University of Oldenburg, who have managed the production of a lot of these European versions of the test, was to record each two-word pair in order to preserve those co-articulations. So one list of 100 sentences, you can contain all two-word pairs. For example, Amy bought, Amy gives, Amy got, and then bought two, bought three, bought four. And that preserves the co-articulations and that creates sentences that sound seamless. So those versions of those sentences that I played you just a moment ago were all recorded with that technique. So here's an example of how it works. We take a sentence like Amy likes 6 old books, and you break that down into its two-word pairs. You have Amy likes 6 old, and old books, and each of those is its own WAV file, and then you play them together. You concatenate them. So here's what they sound like individually.
Amy likes 6 old books.
Now you'll notice that the breaks between those WAV files don't correspond to the breaks between the words, but what it means is that the sounds are segmented such that they can be maximally joined to the subsequent words. And when we play these together, you get...
Amy likes 6 old books.
You can see it's completely seamless. Here's another sentence. Oscar sees 12 good shirts. Oscar sees 12 good shirts. Each is its own WAV file. And what we have is...
Oscar sees 12 good shirts.
In the 12, there was a little g sound there. That means that that could be used for good bikes, good books, good shirts, any of those it can just attach onto there. And again, both of those sentences were never actually said by Emma, our speaker. All right, so...
Oscar sees 12 good shirts.
All right, so what we did then was... the student that I had working on this and who did that editing, he was Ron Trouncin, and he did an absolutely fantastic job developing those stimuli. And so we had the whole year to do that study, but he knocked it out of the park in just a couple of weeks. And so I thought, well, I mean, that's a bit easy. The next step would typically be to go ahead and normalize all of those fragments. But that work coincided with a visit at the time by Nancy Ty Murray, who was in our department teaching at the time as an Erskine Fellow. And so we were talking a lot and thinking a lot about auditory-visual integration at the time, because as we know, speech perception is an inherently multimodal phenomenon. We're readily able to integrate speech information from the auditory, the visual, and even the somatosensory modalities. And in terms of speech reading, we've got visual cues that provide information about the acoustic speech signal that improve our performance in difficult listening conditions. And assessment of that speech reading ability can provide valuable information regarding an individual's communication ability that gives us more information than we're able to get just from the audiogram or just from speech audiometry in the auditory-alone mode. And we can also use it as a tool to measure the outcomes of oral rehabilitation programs, for example. So I knew a bit about programmatic video editing, and Ron had demonstrated his editing prowess. And so those considerations led us to revise our aim and think, well, maybe we could join together fragments of video in the same way that we did those fragments of audio. In other words, could we design and record an auditory-visual matrix sentence test that was suitable for use with speakers of New Zealand English? We knew it would be difficult, but we thought we'd give it a go. So what we did is we took our speaker, Emma, and we anchored her head in place as best we could. The slightest movement would ruin the transitions that we needed to make between each of those cuts. And the human eye is really good at identifying things that are sort of wrong with video. So we recorded in front of a green screen, and we presented 100 sentences for her to read via an improvised auto cue made out of a piece of glass, a cardboard box, and an iPhone. So Emma did a remarkable job at keeping absolutely still and reading those sentences off the auto cue, looking direct into the camera. And we recorded that in high definition video at 50 frames per second to give us a greater degree of precision when it came to the editing. And then Ron locked himself away for a solid week to segment the material into its two-word pairs using a number of different rules to ensure that we match not only the sound, but also the mouth position and the facial expression. We went then through a process of post-processing to prepare that material for integration into our custom written measurement software, which you can see here. And so here's the finished product. I'm going to play it to you now. Just keep in mind that none of these sentences were actually said by our speaker. These are all synthesized sentences.
Amy gives 9 dark shoes. David sold 9 red mugs. Hannah likes some large spoons. Oscar kept 10 green mugs. Oscar sees those large toys. Peter gives 9 cheap hats. Rachel sold 12
Right, so you get the idea. I mean, it's pretty remarkable. We were really happy with that outcome. There were a few instances, though, where there was a bit of a visible jump, and so we needed to set ourselves the task of weeding those out. And you can do that by just mathematically subtracting one frame from the next and look at the difference between the frames. And so here's an example of a good sentence.
Amy gives 9 dark shoes.
And on the plot here, you can see the degree of difference between frames. And here's an example where we have a bit of a jump in this sentence.
David gives 8 large mugs.
The point where the jump is corresponded to a large increase in that difference. And we can rank those transitions and just exclude the ones that are not performing. So here you can see we've rejected the worst 10%. And that's given us greatly improved the reliability of that video. But we also wanted to subjectively ensure that all of the ones that made up our lists also were up to snuff. And so we ran those past another bunch of participants, 18 young adults, who subjectively rated the degree of judder of those sentences. And we were then able to exclude those sentences and replace them with others. Okay, so then we've got to go through the process of normalizing them in the auditory alone condition. And now we mentioned that we've got those 5 by 10 word matrix. We need to get all of the 2-word pairs, and it turns out there are 400 of those 2-word pairs because of the way we slice up the stimuli. And so we had to actually normalize every single one of them using a large number of participants. And so we were able to do this for 2 different types of noise. So the first was constant noise, just like we had with the Digit Triplet Test, created from the stimuli itself, that has the same long-term average spectrum as the stimulus. We also use multi-talker babble, which provides a bit more realistic modulation patterns, which some people like to use. And we also needed to do it for different response modes. So we have the closed set response mode, which is where the client selects their own responses using the touchscreen. And that's very useful for testing clients in their own language. So particularly in the European context, you can be in a German audiology clinic and test someone in Polish, for example, even though you don't speak it yourself, because they're able to score themselves using the closed set response mode. Or we can do it in open set, which is simply where the client repeats back the sentence and you score it as the clinician using a touch screen. And that turns out to be a much less complex task for clients who have working memory problems. So if you think of a matrix like this, visually it's quite imposing. You've got a large number of items to choose from there. And if we hear a sentence, you've got to hunt on the screen, find the word, push it, go to the next one. And by the time you get to the end, you might have forgotten what those sentences were. So here's an example of the finished thing and the closed set response. Thomas likes 3 good books. So you can also use this test in the open set response mode. So here's an example of the multi-talker babble, where you as the clinician are listening to what the client repeats back, and you just score by pushing these buttons. 3 good books, if they get them all correct, or if they do get them all correct, you can just press the all correct button and that automatically scores it as you go along. So the scoring is really very simple. Okay, so we normalized each of those 400 speech fragments, and we found that we were then able to use that to generate lists using an iterative procedure to generate lists that contain 10 sentences each, which we then randomly combined to create a list of 20 sentences that we used for the testing itself. And we adjusted those with that automated process to make sure that they were each equally sensitive and were as homogeneous as possible in terms of the slopes of the tests. So here we have the closed set constant noise. You can see each of those 16 test lists that we generated are indeed equivalent, and they overlay each other really very well. The open set response mode is a little bit harder. We need to go to slightly easier signal to noise ratios to get 50% correct. But again, you can see those are remarkably consistent. So we're very happy with the way that list formation has turned out. And they also compare very well to the other international versions of the test, both in constant noise in the closed set and the open set environment. So our test is the one shown in black here. So I mentioned that it was an adaptive procedure. It's not a simple one-up, one-down procedure that's used. It's an adaptive process developed by Thomas Brandt and Birke Kohlmeier. And you can see there are two examples of it here. The single adaptive track mode concentrates on finding that SRT value, but doesn't really care about slope. You can do that in about 4 minutes. Or you can use a dual adaptive track mode to find not only the slope, not only the SRT, but also the slope, which is quite valuable. And that takes slightly longer. It takes 6 minutes to get that information from 30 sentences. So it's a tremendous amount of information, and it's exceedingly reliable. You can see these two different presentations with the same participant were within 0.4 of a dB of each other. So it's a really well-performing test. But as I mentioned, it is demanding for people with auditory memory problems. So you've got to hunt across this wide array here. And we actually want the test to be able to be used by children and also by the elderly. So to do that, the approach that's taken overseas in a lot of different places is to create a version of the test that doesn't impose such significant cognitive demands on participants. And we did that by creating a simplified matrix sentence test, which reduces the 5-word sentence down to a 3-word pseudo sentence, and also reduces the amount of choice for each item to reduce the cognitive and linguistic demands. So some examples of European matrix sentence tests with simplified sentences are shown here. So 5 weiße Blumen or 9 ballons rouges, for example, are just sort of fragments of sentences, if you like, pseudo sentences. So for our simplified version, we created a 3x6 matrix from the last 3 columns of the test. So we discarded the first 2 and had the last 3. And we prioritized those words that had a lower lexical difficulty, had better psychometric slopes, and which required less editing, because we used the same stimuli that we recorded for that adult version of the test, and we just edited it differently. So here's our simplified matrix that you can see here. And this is the work of Pace Jenkins Foreman, who did a fantastic job of creating this stimuli, and it sounds like this.
10 old books, 8 red spoons.
So with our 3x6 matrix, we have 6 to the power of 3, or 216 possible pseudo sentences. It's not 100,000, but it's still a lot. And we, after discarding ones that didn't work as well as they could have, we evaluated the psychometric properties of 162 of those pseudo sentences. And again, we generated test lists that were really remarkably consistent and homogeneous in terms of their SRT and their slope values. Some of the criteria that we used were to ensure that we didn't replicate any 2-word pairs within a sublist. And then we take 2 of those lists and combine them randomly during the testing to provide enough material for whatever adaptive process it is that we're doing. So we evaluated those lists, and we found results between the lists. In the open set auditory-alone mode. We don't tend to use the closed set mode with the pediatric clients just because they've got to, it's too difficult a task. But we then went ahead and looked for the effect of maturation on the ability to do this task with this set of lists. And we used 125 normal hearing children, in primary school age children, aged 6 to 12, and we presented the stimuli in the auditory-alone mode in the open set response, where they just repeat back what they heard. And when we looked at the scores and the improvement that you get with SRT with age, we found that the scores tend to plateau above the age of 10. So at 10 and above, it's essentially you can use one set of norms, but you need sort of age-appropriate norms for the ages below that. So we had no significant effect on the speech reception threshold on a variety of demographic factors, including household income, ethnicity, presence of other disabilities, or whether the child was meeting educational standards or not. All right. So the other thing about this simplified matrix test is we can also use it to as a diagnostic test for pediatric populations, but also elderly populations. But it's also uniquely able to present auditory-visual sentence stimuli, and therefore it shows promise for measurement of auditory-visual integration in pediatric clients as well as cochlear implant populations. So the way that works is you generate your SRT and your psychometric function for that person. You find the signal to noise ratio, which you expect them to get 30% correct, and then you add in vision and you look for the enhancement in their scores that is provided by that vision. And so that's a standardized measure that's often used by people doing this type of research. Here's an example of what that visual stimuli looks like. All right. Now, we also generated this test in Malay. So we mentioned that 270 million speakers, it's lacking a heap of speech material. With Saiful Jamaluddin, we had the aim to replicate this process. So not only have we created the first auditory visual matrix sentence test, we also created the second and the third. Our goal was to develop, normalize, and evaluate an auditory visual matrix sentence test in Malay. So the Malay word matrix was taken using a bunch of bisyllabic words that are selected based on their familiarity, neutrality, and had the appropriate phonemic distribution. And instead of the New Zealand English matrix and the British English matrix, so here's the phonemic distribution. You can see it matches the typical Malay distribution of phonemes quite well. The order of the words is slightly different compared to English, where we have the object and the adjective are in different positions. So Malay is similar to French and Maori in that respect. So here we have subject, verb, number, object, and then adjective. So an example of a sentence, if we translate it, is Mum gives 3 red tables, or we have 2 green knives. So we recorded this test. This is the final matrix that you see here. We recorded it using Nerlin, who was one of our PhD students, who was a 33-year-old female with a typical Malaysian Malay accent. But here's the fantastic bit. When it came to recording the auditory visual stimuli, Nerlin wears a hijab. And so we're able to take advantage of that by creating a plaster cast which locked her head and shoulders into place. And then we bolted her to the wall. And you can see here she's even strapped to the chair, and we put her hijab over the top of that. So here she is there. She looks like she's sitting rather comfortably, but she's actually rigidly fixed to the wall. And that had a tremendous impact on the quality of the video that we were able to record from her. She did an absolutely fantastic job. And the video is even better than the New Zealand English stimuli. It's absolutely seamless. So we did the typical video processing with mats and a bit of color variation. And here's what the final result looks like.
Kami nampak semua pisau kecil. Abang ambil 3 kotak hitam. Kakak minta 8 topi cantik. Kita beri semua meja kecil. Abang minta 4 topi hitam.
Absolutely fantastic. So that's the auditory visual matrix sentence test. So to conclude, our auditory visual matrix sentence test holds promise as a multimodal test of speech perception. It's easy to administer, it has high face validity, and it's able to be normalized both in New Zealand English and in Malay. And presentation in the auditory alone, vision alone, and auditory visual modes allows assessment of an individual's auditory visual integration abilities. Okay, so the final test, thank you for sticking with us this long. The final test I want to talk to you about is the UCAST-FW, the University of Canterbury Adaptive Speech Test Filtered Words. The project was carried out by several Master of Audiology students, starting with Andy McGaffin, and a number of students over a number of years, as well as my absolutely wonderful colleagues, Natalie Rickard, Megan McAuliffe, and Rebecca Kelly-Campbell. So one type of test that's commonly used to assess auditory processing disorder is, or APD, is the filtered words test, dating way back to the 1950s. And that's where you filter a monaural low redundancy speech sample to distort its frequency content. So for example, here is an example of filtering.
Dog, dog, milk, milk.
And what we find is that listeners with APD typically show an impaired ability to recognize speech when parts of that signal are missing. So, as you can imagine, if this phenomenon has been known since the 50s, there's a wide variety of those tests out there, but all of the existing variations of the filtered words test have limitations. And they're typically because they use a constant level of low-pass filtering in a number of cases. So, for example, a fixed 1 kilohertz cutoff frequency, and that makes them vulnerable to ceiling or floor effects. It's either could be too easy or too hard. The test isn't as accurate, as efficient as it could be, and that results in poor sensitivity and a task that's relatively non-engaging. We've modified this process by creating the first adaptive low-pass filtered speech test. So here's an example adaptive track where we have filtering that reduces by a certain percentage every time you get it correct. The filtering gets more severe. Every time you get it wrong, it gets slightly easier, and we go backwards and forwards and find the threshold at which you achieve a certain criterion score. And we calculate it in much the same way as you would do with other adaptive tracks. So it's a 4 alternative force choice picture pointing test that uses pictures, such as you can see here. The stimuli that we use are the new chips stimuli, and you can see here that the pictures that are used in that test were drawn quite some time ago. That shoe looks straight out of the 70s, and I was presenting this, and my head of department at the time, I said, look at this shoe. It's ancient. It's and he pointed down, and he was wearing exactly those shoes. So I was quite embarrassed. But yeah, so it's a 4 alternative picture pointing task. This is the screen that the kid sees, and you can also do it with words instead of pictures. And then the clinician has a different view of the software that controls the test processing, and you've got buttons here to encourage them, give them a bit of a thumbs up, and keep them going during the test. And then you get the adaptive tracks that you see here. So with Natalie Rickard and Uta Heidke, we published results of tests that we had done with a number of children with and without APD. So children with no sign of APD and those who had tested positive on an APD test battery. And here's some example tracks that you see here. So on the left side, we've got controls, and you can filter out quite a lot of that speech material, and they'll still get, 2/3 of them correct. So here we've got filter frequencies of 340 odd hertz or 500 hertz. But the children on this side all have failed the APD battery, and you can see that they require much higher degrees of frequency content to be provided for them to achieve the equivalent score. And when we look at the groups, the control group versus the APD group, you can see there's a real clear difference between those two that's highly significant. When we look across individual participants, you can see, though, that there's still quite a bit of variation between the individuals there. And I mentioned that one way that we improve the variation of tests such as this is through that normalization process, making each of the stimuli equally difficult. And that hadn't been done with this particular set of stimuli. It wasn't ever designed to be administered in this mode, and so it hadn't been normalized. But that really gave us the thought that, well, we actually should go ahead and normalize this. When we look at your performance on the UCAST-FW, of course, it's sensitive to your auditory processing abilities, but it's also dependent on the level of filtering of the word and the spectral composition of that word. So if a word contains a lot of high frequency content, it's going to be much more vulnerable to that high low pass filter than a word that doesn't contain as much filtering. So a given level of filtering does not produce the same level of word recognition performance for all the words. So for example, meat and shoe would perform quite differently given the high frequency content there. All right, so how do we normalize this test material? As we said, we've already spoken about normalization. You make all the items equally difficult, and that sharpens the slope of the test and makes it a much more sensitive test. But what can you do for a filtering test? So here's the speech and noise example where we shifted them together and the curves now overlay. How do you normalize a filtered words test? You can't sort of pre-filter or unfilter words. That posed a bit of a challenge. So what we decided to do was evaluate the degree of heterogeneity of the UCAST-FW word list under conditions of low-pass filtering, and to try and develop a normalization process to compensate this. And this was the work that I did with Jasmine Gibbons. So because we can't pre-filter the stimuli, instead we've got to make judgments based on our knowledge of the psychometric function of each of these items. So here you can see psychometric curves for the word duck, and also for the average across all of the words in our test battery. So for a given word and a low pass filter frequency, what you have to do is calculate the required correction towards the mean and adjust the filtering accordingly. And you do this in a way such that the adaptive procedure doesn't see the actual degree of filtering, just what was the intended degree of filtering based on what the next step in the adaptive procedure was. That part is very important. I'll talk you through an example. So let's say the next item in the adaptive track is to be filtered at 700 Hertz. We've done our adaptive track and the next item needs to be presented at 700 Hertz. And the particular word that we're presenting is duck. Now, when we look at the performance of duck at 700 Hertz, you're going to get about 98% word recognition for that. So that's quite an easy word to receive there. And that's going to throw out the adaptive track because you'll be too correct. But the average word recognition performance at 700 Hertz is only 76%. So there's a difference there. So what we need to do is to make the performance of duck closer to the average. We need to figure out the amount of filtering that we would need to apply to duck to get that same score. So what level of filtering would we need to achieve a score of 76% correct? Well, we've got the formula here for the psychometric functions. All we do is reverse those and solve for that value. And what you get is this. So here you can see 517 Hertz is the answer. If we filter the word duck at 517 Hertz, we get the same response that we would get for all the other, the average response if we filtered it at 700. Now, the beautiful thing about this is we lie to the algorithm and we say, oh yeah, no, it was 700, but in fact, we've sneakily gone off and filtered that item at 517 Hertz and the algorithm is none the wiser. Does that work? Does that have an effect on the how close together and how bunched up those psychometric functions are and the sensitivity of the test? So our aim was to determine how different items in the UCAST-FW word list perform with low-pass filtering and to develop a normalization process to compensate for that and to evaluate the effect of that normalization. We also wanted to compare open set and closed set response paradigms and determine whether any of those words were just not good performers that should be sort of eliminated entirely. All right, so here's our results. You can see pre-normalization, it's pretty messy. Post-normalization is an improvement and there are outliers within there. So 7 of those items didn't improve at all and so we discarded them from the test. And here is our post-normalization set of lists. You get an idea of the spread of those low-pass filter frequencies being greatly improved. So by excluding the outliers and performing that normalization, we've reduced the standard deviation at the midpoint of those low-pass filter values by 46%. So that's greatly improved the performance of that test. So this is in the closed set condition. It's similar results in the open set condition. And on the whole, the open set performance was much more homogeneous and reliable than the closed set. So that's our sort of preferred mode of delivery. We also, this test has been published for a little while now, and you might hear Suzanne Purdy and Bill Keith talk about the New Zealand APD standards that have been developed. They'll be talking about that in a couple of weeks as part of this conference series. So in 2017, the New Zealand Ministries of Health and Education Expert Reference Group for APD recognised the UCAST-FW as being suitable for use by audiologists in New Zealand. They noted that it had acceptable test-retest reliability, established validity, and it demonstrated a good sensitivity and specificity, clinical acceptability, and published studies. But they noticed that the significant maturational effect that was seen in the the initial study that we had would need to be sort of quantified in a bit more detail in a larger sample to get some more normative data. So in 2018 and 19, 2 of our students set out into the high school, primary schools and gathered normative data from 143 normal hearing English speaking children aged between 6 and 13. And this is what we found. Here's the spread in the left ear and in the right ear for their monaural low-pass filter thresholds. So what you can see is that when we divide, take into account all of those different demographic characteristics that we gathered on the children that I mentioned earlier, of those, age was the only significant predictor of low-pass filter threshold amongst this bunch of kids. So what you can see here is if we do a cluster analysis, we can divide them up into 3 age groups. And what we found is that there is a significant effective maturation that occurs between those first 2 and between the first and the last age group there. So we're still on the way to getting age appropriate norms that we can use. We need an even larger sample for that, but it was sort of reassuring to see that this data matched quite closely the maturation data that we had gathered with Andy McGaffin and Natalie Rickard as the first of these studies on the UCAST-FW. So here's the effective maturation that we found in that study, and if we take this new data and overlay it, you can see not only does it follow it, it's a much higher correlation as well. So it shows that there is a significant maturation effect there. All right, so we've reached the end. In summary, we've created a novel method of normalization for low-pass filtered speech tests to compensate for the spectral variability and differences in word intelligibility under the same levels of filtering. And in doing so, we've successfully achieved a more homogeneous word list, resulting in a more normally distributed cluster of psychometric functions. And the first normative data has been gathered, and there's more data to come in 2020. No, sorry, it'll have to be 2021 now, given the way this year has turned out. All right, so what's next for the UCAST-FW? Well, currently, you might have guessed from the pictures that I showed you, it's currently using the NAL recording of the new chip's test stimuli. So in other words, we're currently testing New Zealand children with an Australian recording of an American test. Now, you can imagine that's not ideal. So take, for example, this picture with an American accent. They've all got the same phoneme. We've got frog, dog, ball, car. But in an Australian accent, it's frog, dog, ball, car. It's not working in the same way that we would like. So with Sarah Murray, we've created a new alternative forced choice word list for New Zealand English that's designed to avoid things like that. And we might create that as to replace the current stimuli. But we're actually thinking that what we might do as a next step is to take the pediatric version of the matrix sentence test and low pass filter that, use that as the stimuli instead, because it has a heap of advantages. We have more scoreable items, which means we, instead of 1 word, we've got 3. And that gives more efficient adaptive tracks and enables us to do presentation in the auditory-alone and auditory-visual test modes. Okay, and what's next for the overall UCAST platform? Well, currently we're working with colleagues in the School of Product Design at the University of Canterbury to enable this to have a wider public release and hopefully get it into audiology clinics throughout New Zealand and Malaysia and further afield. So thanks very much to you for listening to this presentation. I'd like to thank all of the people who are named here, and also in terms of financial support, I'd like to thank the Oticon Foundation in New Zealand, who have provided a tremendous amount of financial support over the years, as well as Resound. So that's it. Thank you very much for listening.